let us consider this curve given by x equals sine t, y equals cosine t, and z equals t. This is a circular helix. Now, if we differentiate r with respect to t, then we get cosine t negative sine t1 as the components, and this will be along the tangent to this curve at the point corresponding to t. Now, if we consider the motion of a particle along this path, then let's use the fact that this is in the direction of the tangent to develop a frame along a point corresponding to each t. Okay? So if we multiply this tangent vector to the curve by reciprocal of its magnitude, what we will get? We will get a unit tangent vector along the tangent line. So what we are going to do is that we are going to denote the unit tangent vector by this symbol t hat t, and then we shall use the fact that this t hat t is a unit vector to obtain a normal vector by the following procedure, that we shall go ahead and differentiate this equation with respect to t. So we differentiate by using the product rule for dot product and get this equation. Now we know that the dot product is commutative, so these two quantities are equal and they add up. Now division by 2 gives us the equation that t dot the derivative equals 0, and which tells us that the derivative of t hat is a vector which is perpendicular to t hat. And t and its derivative are at right angle. And now if we do simply this, that multiply the derivative of t with the reciprocal of its magnitude, we get a unit vector. Let us call this unit vector, so n. Okay, so if we look at these three vectors, t, n, which are unit vectors and are perpendicular to each other, and form this vector t cross n, first of all, this will also be a unit vector, and because t is a unit vector, n is a unit vector, and these are at right angles, so sine of 90 degrees is 1. So here we have a set of 3 unit vectors at the point pt. So let's take just a quick graphical illustration of how they look if we graph them. And what we would do for the graph is that we shall give a particular value to t and look at the point and the graph of, or a sketch of, these 3 vectors at that point. All right. Now before going ahead, let's give this unit vector another notation. So let's call this vector b. So we got t, n, and b, 3 mutually perpendicular unit vectors, giving us a frame at the point p corresponding to t. Okay. So we could choose any value for t, but I'm choosing pi over 2. And again, you can choose any value, and that is for computational convenience. So if I take my t as pi over 2, then what r prime t will become there? So r prime pi over 2 is going to be, so let's just substitute t equals pi over 2. Okay, so what we shall have? We shall have cosine of pi over 2, right? Then sine of pi over 2, okay? And then cosine of pi over 2 is 0. So we will have that as 0, cosine of pi over 2 is 0, sine of pi over 2 is 1, so we get 1, negative 1, 1 as the value of as r prime at pi over 2. Now let's write its magnitude, okay, that of r prime at pi over 2. What that will be? That will be simply, we have first component square. I'm just formally writing it as 0 square plus negative 1 square, which will be 1. Okay, feel free to fast forward if you would like. Then 1 square, and the whole thing becomes a square root of 0 plus 1, that is square root of 2. So what the vector t will be then? Our vector t will be, or t at pi over 2 is going to be 1 over square root of 2, because that's the reciprocal of the magnitude, right, times this vector. Okay, now let's compute the vector n. Okay, how did we obtain the vector n? We obtained the vector n by differentiating tt. So first let's write tt. Okay, so how do we write that? We not at pi over 2. We have to write it here in general. And in this case, it's a coincidence that the two of them are the same. That is, even if you compute the magnitude of r prime t at any t, then because of the Pythagorean identity, that we will have cosine square t plus, then we have negative sine t square, which is going to be sine square t. All right, and the two will add up to how much? 1, and then we will have 1 square. So in this case, again, it is just a coincidence that this magnitude of r prime t turns out to be a constant. Okay, so how would we form our tt? We would do this, that take the reciprocal of the magnitude of rt, all right, and multiply it by, so I meant r prime t, multiply it by r prime t then, and then how do we obtain nt? We'll just go ahead and take the derivative of t, capital T, with respect to the parameter t. All right, and what that will become, this being a constant, stays as it is. All right, and then we have negative sine t as derivative of cosine t, then negative cosine t, and then the third component would be 0. So what does that give us? That gives us that the magnitude of t prime is how much? We will have 1 over square root of 2 here. And since we have done quite a few of such calculations, let me not just write down every detail. We'll have a square root of sine square t plus cosine square t, which is going to become 1. By Pythagorean identity, 0 is not going to make any difference. So this will be 1 over square root of 2 times simply 1. So what my n will be? Okay, my n will be at t then. That will be the reciprocal of t prime t, which is going to be reciprocal of 1 over square root of 2, and which is square root of 2. And when you multiply that with this, this will cancel. All right, earlier I was writing every little detail. I hope you don't mind me skipping that here. And then if we compute that, or if we calculate that at pi over 2, what shall we get? We shall get sine of pi over 2 will become 1. So we get simply -1. Cosine of pi over 2 will be 0. So that stays as 0. And the third component is already 0. And now we would like to obtain our b, which we may call a binormal vector. Okay, I'll write it down for you. So b is simply t cross t cross n. Okay, so let's write that down. We got t cross n. Now if we write it at pi over 2, okay, I'm going straight there then. Okay, so if we write it at pi over 2, this will be t at pi over 2, right? And then n at pi over 2. All right, so t at pi over 2 is what that will be. That is going to be, we just computed it, 1 over square root of 2, right? So we got 1 over square root of 2. And why don't I just go ahead and paste our t at pi over 2 here, 0, -1, 1. Okay, so this is this right here, and then my n is this. Now you can use the method of determinants, or which let me write that determinant here for you. I have been skipping a lot of steps, so maybe just write those here. So you get I, j, k. Okay, if you compute it in this manner, and let's just write 1 over square root of 2 outside. Okay, so here we are, and then we get 0, -1, 1, 1, 0, 0. So what shall we get from out of it? Okay, we shall get simply 1 over square root of 2, right? And then after that, let me just write the other steps. Here you can see these two will multiply to 0, so we simply get 0, then comma, then we will have -1 because here we'll go in the reverse direction. So get -1 here, and then when we go for k, 0 times 0 is 0. This negative time, -1 times 1 will be 1. So who will be our b at pi over 2? That will simply be, so b prime of pi over 2 would simply be 1 over square root of 2, 0, -1, 1. All right, so here we got the frame of reference here. This is our tangent vector, normal vector, and this is binormal vector. So let's go ahead and see how their sketches will look like on the curve. Okay, so here we got our helix, and the coordinates of the point P at pi over 2 will be 1, 0, pi over 2. And here we got the tangent, normal, and binormal. So if we graph that in MuPad, and as I said, I'll post a separate video showing you the details of graphing it in MuPad. So here the three vectors are at the point on the helix, and they don't look mutually perpendicular. I guess we have to take equal axes, sorry, equal length along the axes. Okay, and here it is. All right, so here they give us a, yeah, they give us three mutually perpendicular vectors. So let's go ahead and zoom into this portion. Okay, so here are our tangent, normal and binormal vectors, and I shall show you in a separate video that the principal normal vector will point towards the concave side of the curve. All right, so yeah, I'm going to show you a reason for that. So again, this is tangent, this is normal, and this is the binormal. Now here the same vectors are in a little bolder format, so we'll continue with this in a separate video. All right.